Okay, so this is last spring's test, spring 25. Okay, so as I was telling you before, every test has got three parts. Naming structures and structure naming, intermolecular forces, and reactions. Okay, so we're going to be naming this now. Okay, so I want you to be really careful and distinguish between this one here and this one here. Okay, because this, has a benzene ring in it. It's called phenol base. And it has a branch at branch 2. So it's 2-propyl phenol. Propyl because we have 1, 2, 3 carbons there. If you have a question, just talk up, okay? All right, identify the backbone first. The backbone has to include the functional group. Notice instead of going straight across, we had going straight across would not include the functional group. So this is 9 carbons. And if we start up here for numbering, we're going to get the functional group as carbon number 1. So that's where we're going to start. And then this is going to be carbon 9 here. So carbon 2 has got a methyl branch, 3, 4, 5, 6. It's got a propyl branch. So it's going to be nona-all. And it's 1 nona-all because the hydroxyl group is on carbon number 1. So we have a methyl and propyl. So the methyl is going to come before propyl. And squeeze that propyl in there. So it's going to be 2 methyl, 6 propyl, 1 nonenal. Now here we have a ring, 6-membered ring, but it is not benzene based or aromatic because there's no circle in the middle. So it's six-membered. So if we start here in the functional group, so that's going to be cyclohexanol, and it's going to be 2 propyl cyclohexanol. Now, if you put a 1 cyclohexanol, that's fine, but you don't need to put it. It's assumed to be a carbon 1 if you put no numbering there. Okay, now this one is a little tricky. Okay, backbone is going to be this 2-carbon alkene. So that's ethene. And we have 2 branches. We have 2 aromatic branches. Now, when aromatics are branched, they're called phenols. So that's 1, 2 diphenyl ethene. Now, we can say 1 ethene if you want, but there's no way it can be anything else except 1. So if you want to put the 1 in there, that's fine. So it's consistent. Yeah.
What if we put it all together?
Put what all together? Yeah, you mean without dashes? I just put the dashes into, so you can tell them apart pieces. If you want to put it all together, that's fine too. Okay, but we're not done yet. We have to distinguish between these two. They're not the same molecules. This is cis and this is trans. Cis means they're together. Trans mean they're opposite. Think of Transcontinental Railroad. Apart. Cis, think of sisters. Um, the problem with cis and trans is three-dimensional, and we write on two-dimensional devices, whether it's paper or the screen. So I'll put real simple examples on the test, so you should be able to go. But you can always do it, if you have a big long string, it's frequently trans, because that's more stable than cis. But think about the simple one for cis and trans. And I put careful on there just so you kind of hint there's something going on here. That's one indication for sure. Frequently you'll have methyl groups like this. Yeah, cis and trans. This is happened to be phenyl groups. But normally it's going to be the same. Like if we had this, it wouldn't be cis because one's an ethyl and one's a methyl. Normally it's the same. Okay, draw the following structures. Okay, so we've got heptene, that's 7, and it's a alkene. And the double bond is a carbon number 3. And we have a branch on carbon number 3 of phenyl. And we have on carbon number 6, 4, 5, 6, we have 2 oral groups. So this is carbon number 6. Okay, we doing okay? All right, let's look at this one here. Cyclohexanol. Okay, now the 6-membered ring is the most stable of all the rings. That's why frequently in natural occurring things, you'll have 6-membered rings. For example, the carbohydrates are all based on a 6-membered heterocyclic ring, which means it's got carbons and oxygen. It's still 6-sided though. Now, 5-membered rings in nature are pretty solid as well, not as stable as 6-membered. Like fructose, for example, is a 5-membered heterocyclic ring. Okay, and it's an alcohol. So that's automatically going to be carbon number 1. Backbone. And we've got a carbon number 2. We have a methyl. Carbon number 3, we have an ethyl. All right, we've got another cyclohexane. The backbone is automatically the cyclic group. And we have 3 methyls. Now make sure you pay close attention to that cyclo. Frequently, students forget about this cyclo. Okay, hexanol. And we have carbon number 2 is where the alcohol is. And on 3 and 4, we have methyl branches. Okay, intermolecular forces. Okay, we're going to use oxygen a lot in this semester. Whenever you see oxygen, I want you to think polar. Now, if we look at ethanol, let's list all the intermediate molecular forces. Okay, LDF, London dispersion forces, is the weakest of the intermolecular forces, and it's in every single molecule, no exceptions. So you immediately put down LDF, whether it's alkanes, alkenes, alcohols, ethers, aldehydes, ketones, acids, amino groups, LDF, boom. Now we've got an OH, that's hydrogen bonding. Hydrogen bonding is extremely strong. It's only second to an ionic bond. So alcohols are very, very, very polar. It's also got a carbon-oxygen bond, which is a dipole. And that's not as strong as the hydrogen bonding. So those are the 3 intermolecular forces for, if it's an alcohol, it'll have hydrogen bonding. If it's an ether, it's still polar, but not as strong as an alcohol. It doesn't have any hydrogen bonding. It's got carbon-oxygen bonding and carbon-carbon bonding. And then, of course, LDF, alcohol. So if it's an alcohol, extremely strong, very polar. So that means high boiling point, high surface tension, high melting point. If it's got an oxygen in it, but no H attached to it, it's still polar because it's oxygen, very electronegative, but it's not as strong as an alcohol, like an ether. It's got a COC. So it's got the oxygen there, but there's no hydrogen attached to it. So it's not as strong as the hydrogen bonding one. But if it had an alkane and an ether, ether's stronger because of the oxygen. Alkanes are the bottom. They're very milquetoast, very, very nonpolar. Exactly. Just LDF, London dispersion forces, is all it's got. Same with an alkene. London dispersion forces. I don't like busy work. LDF. You can write it out if you want. Same with hydrogen bonding, H bonding. You can write out hydrogen bonding if you want. That's fine. But H bonding works. Okay. All right, it says correct the following chemical name. All right, let's draw it as written. Okay, so we have butane. Okay, and then on carbon number 3, we have ethyl. Let's do this. Okay, so that's the structure as written. The name is wrong. What should the name be? Well, first thing, we do the backbone. Okay, so how long is the backbone? 1, 2, 3, 4, 5. So this should be labeled pentane and a branch at carbon number 3. So 3-methylpentane. Okay. Reactions. All right, so whenever we have a reaction, make sure you name everything. Products and reactants and conditions. If there's a mixture, circle the most stable one and run the 2 stability tests, Markovnikov, terminal hydrogens, and then symmetry. And I suggest writing a sim, X or checkbox, and mark or Markovnikov, if you want to spell it out, X or check mark. Okay. All right. So what we got is I need to put a flow chart over here. Let's see. Where is where's the insert?
Yeah.
Okay, so we've got an alcohol with under acidic conditions. Or H2SO4. Either one's fine. And the same structure, this alcohol undergoes a reaction at 140 and 180. They are not the same thing. So let's find that on the flow chart. Okay, so we've got an alcohol and it's undergoing dehydration under acidic conditions at 140, which forms an ether, and at 180, which forms an alkene. Now, this tells you how stable the alcohol is compared to the alkene, because we've got to add a ton of energy to make this happen. And what we're going to do, we're going to pull off water. So this is going to be plus water. Now, frequently with the alkene, you get a mixture. Okay, so let's go over here now. And let's do the ether one first. Now, 140 produces an ether. An ether simply is, and it takes 2 of these. An ether simply is the alcohol OH groups stick together. So we've got 1, 2, 3, 4. That's one of them. And then the other one, we're going to flip 180. Okay, so this is going to be a butanol. With a methyl group at carbon number 3. So it's going to be 3,2-butanol. Okay, the ether. So the ether now is going to be made up of 2 butanols. So it's going to be di-2-butanol ether. Now that's the common name. The other name, the IUPAC name, is a alkoxy derivative. And let's just use a common name for ethers because can get really abstract if we use the alkoxy derivatives. Okay, so it's a di-2-butanol not butanol, butyl. Ether. And then water. No mixture. No, the water, no, the water is not part of the name. That's just part of the structure. So in other words, over here, if I had more room, up there. And you can say water if you want. Okay, so the ethers are the trickiest of this group. Because you have to take, and you're always going to flip one of the two 180. So you can connect up the OH groups. Okay, so what comes off is water. So we have two H's that are eliminated and an oxygen. That's H2O. Okay, down here, we've got same 3-methyl-2-butanol, only under harsher conditions, 180. So what's going to happen is we're going to pull off water directly on an adjacent carbon. Okay, so here's the carbon that the OH is attached to. Okay, on an adjacent carbon, is there an H? In other words, is there an H here? Yes. In fact, there are 3 of them. Is there an H over here? Yes. There is 1, but it's an H. So we can get 2 waters coming off here. That means we're going to have 2 different alkenes. So we're going to get one like this. So let's do it in, one's going to be like this. That means this is going to be the double bond. If we do it this way, this is going to be the double bond. Okay, so let's do the black one first. Okay, so we're going to pull off water. And we can also pull off water using the other carbon, the blue carbon. Okay, so we've got a mix. We've got to figure out which one is more stable. So we're going to use 2 tests. Markovnikov. And symmetry. Okay, so Markovnikov, we're looking at terminal hydrogens. So we've got 3, 3, 2. 3, 3, 3, 3. So the one on the right, the blue one, has got a lot more terminal hydrogens. So Markovnikov says it's more stable. Symmetry. The blue one is balanced. It's perfectly symmetrical. The black one is off-sided. So symmetry-wise, the balanced one wins off. So that's the more stable one. And we got to name them. So this is going to be 1, 2, 3, 4. So this is going to be 2. And then on carbon number 3 is going to be a methyl, just like up the top. Okay, this here is going to be an alkene. And I'm running out of room. Let's see. So it's going to be 1, 2, 3, 4. So it's going to be 1 butene. This will be carbon number 1. And then we have 3 methyl, 1 butene. This one's going to be 2 butene. With a methyl group at 2 and 3. So it's going to be 2, 3 dimethyl 2 butene. So any questions about that?
Take the water out. We took off the OH.
We did. We took out the OH. That's where the water comes in.
But for the structure itself, that was.
So we need to take off water. So the OH is always going to be part of the water, but we need another hydrogen to go with to make water. And that comes from the adjacent carbons. In this case, we have 2 carbons that have H's on. Sometimes you only have 1 carbon, which means there's no mix. But if we have 2 carbons with H's on there, you get a mix.
Can I show you? Cause when I did it, I thought this part was the OH group and then we take it off. And then we add the double bond,
That's true.
like
except-
removing this whole part right here.
Yeah, but you pull the water off of here. See, you pull the water off of here as well.
Okay, I pulled it off right here on this carbon.
Yeah, that's
So then
perfect.
this is right.
Yeah.
Okay.
But just that you have to account for this one here as well.
Okay, but if I decide to go with this one, then this is right.
Yep.
Okay. Cause I thought we don't take off this one, cause we need the 3 hydrogens. Like on the end to keep it balanced, right? Or is that wrong?
That's wrong.
Oh, okay.
Okay, so if an adjacent, okay. This is the carbon. Can I draw?
Mhm.
I should have known the answer to that. Okay, so here's an H here. And there's an H over here too.
Mhm.
So once it's gonna be this, the other's gonna be that. So that's what we get to.
Okay.
And then you need to do the Markov and the symmetry test.
Okay.
Is that a little better?
So doing the mark test, it's just about like which one looks more symmetrical, right?
No, that's the symmetry
Oh,
test. Markov is you count terminal hydrogens.
I thought this one we're adding hydrogens.
No, when you're looking at the Markov says, by the way, my structure is not correct. The,
Oh, you're using the wrong pen.
no, gee, why didn't it work? It should be like this.
Yeah, that's what I was asking, because I thought like that whole thing was the OH group and
Yeah, that's in my mind. That's why I drew it that way. So,
Oh,
but I was wrong.
okay.
You were right. Okay, but you have another structure though, which is going to be water this way.
Mhm.
Leaves you with that, but the
Yeah,
double
the
bond.
double bond will be right there.
Yeah, exactly.
Okay. Okay. Thank you.
Okay, let's go on. That was kind of a tricky one. Now on the flow chart, I will tell you, it says expect mix. Most of the time you get a mixture, but not all the time. The times when you don't get a, excuse me, the time you won't get a mix is when the alkene is on carbon number 1. So for example, if we had oops. We have that. So now the alcohol is on the end. So there's only one adjacent carbon that's got a hydrogen on it, which is right here. So that means we're only going to have one version rather than two. So if it's on the end, carbon number 1, so this would be 1 butanol, then 1, 2, 3 methyl. Then you'd only get the double bond at carbon number 1 rather than carbon number 2. So what you'd end up with is that. Okay, so now I'm saying, how do you make this mixture? First of all, what is wrong with this mixture? Now, when I passed out this test last year, I told them this needs that. Wait a minute, see. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. No, I guess not. Never mind. If you redraw this though, like this. Now the backbone sort of looks like this. So these two are the same on the right. All I did was I just flipped it. And on the test, I'm going to flip it for you. So it's obvious what the backbone should be. Does that increase the level of complexity in that problem? That I shouldn't have put that in. Okay, bottom line is, after the reaction, we had a mixture. So let's go to our flow chart. And what produces alcohols? Well, we start with an alkene. We can get an alcohol by adding water across the double bond. So this is the reaction we're going to be using here. Because we have alcohols. How do we make them? We make them from alkenes. We can also make them from an aldehyde or ketone. But that's chapter 2. As far as chapter 1 goes, we can only make them one way. Alkene with water across the double bond. So the double bond, if we start with the double bond going from carbon number 1 and carbon number 2, yes, I was irritated. Okay, so we have carbon number 1, 2, 1, 2. So if we had a double bond on carbon number 1 and 2, we'd end up making these two alcohols. So it's 5 carbons long. So we're going to start with a 5-carbon alkene. Okay, I'm going to put a carbon here. And this is going to be water and either H plus or H2SO4. And that comes directly from the flow chart. Now, yes, I'm going to give you the flow chart with the test. So that means we're going to get a alcohol here and here. So we're getting an alcohol here and here. Let me redraw this one arrow here. Okay, so let's go ahead and name it. This is going to be 5 carbons. So that means it's going to be a pentene. Oops, I got to spell it right. One pentene. And this is going to be 1 pentanol and 2 pentanol. Okay, so does that make sense? Again, we're integrating the flow chart with what we're trying to do. Either you need to make something, or you have something and you throw in some conditions and it's converted. All right, so let's go on here. Okay, we've got 1, 2, 3, 4, 5, 6. So that's going to be a 6-carbon ketone. How do you make a ketone? Okay, we start from a secondary alcohol. Secondary. Okay, so a secondary alcohol that is 1, 2, 3, 4, 5, 6 is going to be carbon number 2. So it's going to be 2-hexanol, and we're going to oxidize it. Now, this is a secondary alcohol. Now, in Unit 2, the opposite of oxidation is reduction. So if you reduce a ketone, you'll end up with a secondary alcohol. If you oxidize a secondary alcohol, you get the ketone. Go back and forth. Same with the aldehyde. Aldehyde produces reduction. You end up making a primary alcohol. If you oxidize a primary alcohol, you make an aldehyde. Now, you don't have to name the ketone other than just saying ketone. Okay, so we have an alkene with a heterogeneous additive, HCl. What do we get? We're going to get a mix normally. Sometimes we don't, but normally we get a mix. Okay, what's going to happen is the H and the Cl are going to add across the double bond 2 different ways, HCl and ClH. Okay, so here's 1-butene. Okay, so one time it's going to be like that. Statistically, the other time it's going to be like this. Now, question is, which is more stable? We have Markovnikov symmetry, Markovnikov symmetry. All right, for sure, the one on the right is more symmetrical. It's balanced. And the one on the left is all jammed to one side. Markovnikov, okay, we've got 3 H's, 2 H's, 3 and 3. So Markovnikov wins 6 versus 5. Okay, so now we're adding a homogeneic additive across the double bond. So no mixture. So the H is going to go here and here. So 1, 2, 3, 4, 5. Now, this is a very slow reaction. So we have to add a catalyst to speed it up. In fact, it's so slow, it doesn't go. So we add a catalyst and it's a normal reaction. Okay, so this is going to be 6-sided or 6-membered. So it's going to be a 2-hexene. And this is going to be hexane.
Would it be okay to draw it without the H's, like this?
Yes, I just did it for. Exactly, yeah. So did everyone understand our question? In other words, do you have to put the H's in? No, I did it just so you know where the H's go. By the way, we can't drink in here. Even though there's no chemicals out, there are no liquids or food in here. Okay, so put it out on the table. And I'll wait for you to get back. Okay, so let's go on. Okay, now this is a two-stepper. First step is we have an alkene and we have we're adding water across the double bond there. So the first thing we get is an alcohol. It's going to be right across here. And let's make this big. Now, when we add water heterogeneic additive across the double bond, we're going to get a mix. So the first thing we're going to get here is the mix. What does that look like? Okay. So the first time it's going to be like this. Second time it's going to be like this. Okay. Everyone see where I got those? We're adding straight across the double bond. Okay, now we're going to oxidize these guys. Now, because we have a mix, we're going to end up with a mixture at the very end because each one of these is going to be oxidized and it's going to end up with a different product. Now, this is a secondary alcohol. Secondary alcohols oxidized produces ketones. So those are the two products you're going to end up with. Now, which is more stable? Markovnikov, they're equal number of terminal hydrogens. However, which do you think is more symmetrical, bottom or top? I would go with the bottom two. The top one's a little lopsided to the right. The bottom one is a little more, it's not great, but it's more symmetrical than the top one. So now on that one, if you got it wrong symmetry-wise, I wouldn't take off any points because that one's kind of tricky. So we have so this is the same. Symmetry-wise, and notice this one's got more points. Okay, and we haven't named it yet. So this is going to be So it's going to be a 1. So 3-ethyl, 1-cyclohexene. Okay, I'm going to run out of room. So for this guy, it's going to be one cyclohexanol, 2-ethyl. And this is going to be 1, 2, 3-ethyl. And cyclohexanol. And we're going to label these ketones. Now, you can leave the 1 off, this 1-cyclohexanol, or you can put it on. I added it for clarity and consistency, but you can leave the 1 off. So if you leave it off, it's assumed the functional group is carbon number 1. Okay, and that's it for reactions. And again, most people find reactions the hardest part of this class. There's FYI. Okay, so we're going to go through here and look at identifying the alcohols as primary, secondary, tertiary, or not at all. Okay, so this is going to be secondary, tertiary. That's because this has 1 hydrogen, no hydrogens, 2 hydrogens. And this is not an alcohol. It's an ether. Now, it's important to understand how to identify them because that determines when they're oxidized, whether you're going to form a aldehyde, ketone, or nothing. So tertiary alcohols cannot be oxidized because there's no adjacent hydrogen on there to come off. Secondary has 1, that means it can oxidize once. Primary has 2, so you can oxidize it twice. Okay, how many carbon atoms does this guy have? Okay, well, here's 5. Here's 2, and here's 3. So we're looking at 10 hydrogens. So let's draw that. That's the cyclopentane. And we have, this is the propyl group. So that's going to be carbon number 1. Carbon number 2 is the ethyl group. So here's 5, 3, 2. So 10 Cs. Why is the study of intermolecular forces important in biological systems? Because biological systems they're extremely complex, number 1. Number 2, because of the nature of the molecules, they're susceptible to the intermolecular forces. In other words, you look at DNA. DNA has 4 different bases, and they have 2 points or 3 points where they line up. And that's strictly intermolecular forces. They're hydrogen bonding there. Either 3 points or 2 points. On the three points, the bases can line up. And again, it's intermolecular forces, hydrogen bonding, or 2 points. Cellular membranes. Those are all there to make polar reactions, which are water-based, isolated. Again, intermolecular forces. So that's kind of where I wanted to go with that. There's a lot of different ways to say that. And I usually gave, if you had some reasonable answers, I probably would give you full credit for that. Okay. What are the two perspectives when determining stability of the molecule? That'd be Markovnikov and symmetry. Okay, so let's look at the molecular forces, intermolecular forces, the following. Okay, so dipropyl ether. Okay, first of all have LDF. So this is going to have dipole-dipole, that's between the carbons and the carbon-oxygen bonds. Hexene, LDF only. Hexane, LDF. Hexanol, that's going to be dipole-dipole and H bonding. Dipole-dipole, that's between the CO, CC, this is between the O and the H. Okay, rank the following. Okay, so this is going to be the highest IMF. Okay, so this is going to be 4, 3, 2, 1. So that means this is going to be the highest. Lowest. Second highest. Second lowest. Yeah, you could have named it 1 being highest, and then it doesn't really matter as long as it's consistent. The two extremes are hexane and hexanol. Yeah.
For the alcohols, you would want us to put both bonds, right? Or the intermolecular forces. Yeah.
Yeah, because I said list all the IMFs. I think that's the end, isn't it?
So then would for hexanol, the one hexanol, we would have to list LDF too? Since you said they all have it.
Yeah, I mean, every molecule has LDF. So on those, the hexene and the hexane, that's all I got. So that's why I put the LDF there. But if you want, see, I put over here all LDF. And you can put the LDF in there if you want, or do it the way I did it. Okay, that's it. If you put hexene as 1 and hexane, because they're extremely close. So those are basically equivalent. It's mainly I was looking for is making sure the alcohol was highest. And then the next one down, the ether is next highest. And the other two kind of a wash between, which is more or less.
Does the double bond have anything to do with the rocket? Yeah. Okay.
Yeah, it makes a double bond is a shorter bond than the single bond. So that means that the C has more interaction, but not by much. But that's to do with the length of the bond though.
Are there any test for us to study occur?
Yeah. It's a whole bunch of them. Okay, so that's it. If you I'm going to end